Hello, my name is Ido Galil. In this talk, I will present the paper, A Framework for Benchmarking Class Out-of-Distribution Detection and its Application to ImageNet. First, let me explain what Class Out-of-Distribution, or COD for short, is. Deep neural network classifiers are trained on data that follows a certain distribution. We define any samples from this distribution as in distribution, or ID for short. In the example below, an autonomous vehicle is trained to recognize signs, pedestrians, and other vehicles. In this work, we consider a COD case where the label set Y changes to a different set that includes new classes not observed in training. In this example, a deer is a class the neural network has not observed in training. The neural network uses a confidence function kappa, such as softmax or Odin, to detect predictions it's uncertain of. This confidence function should rank COD data lower than ID data. Predictions that receive low confidence scores are detected as COD and are treated according to the specific task. In this example, we might expect the autonomous vehicle to activate emergency maneuvers and alert the driver. Now that we understand what COD is, let's consider a scenario where we have a mole and a confidence function that we would like to evaluate. The question is, how should we test their performance? Before discussing our proposed method, let's briefly go over a couple of previous methods. One common method is to use two different datasets. One is used as an ID dataset, and the second dataset is used as an OOD dataset. During testing, we evaluate how well the mole and confidence function can detect OOD samples by assigning them lower scores than ID samples. For example, we might train a CIFAR-10 classifier and test its ability to distinguish images of dogs and airplanes from images of numbers coming from the SVHN dataset. There is, however, a problem with this approach. The datasets used to simulate OOD generally do not resemble a training distribution and, therefore, are easy to detect. The use of such sets can cause COD detectors to appear better than they are. Let's suppose we have trained a dogs classifiers on different dog breeds. We would like to evaluate its ability to detect OOD classes that might include similar classes, such as wolves. It wouldn't make sense, then, to assume the OOD detection performance on images of numbers could also represent the classifier's performance when detecting wolves as OOD. Hendricks et al. Suggested the ImageNet O dataset as a solution when evaluating ImageNet classifiers. ImageNet O, however, has two limitations. First, it benchmarks moles with a single hard difficulty level exclusively, which might not be relevant for every task's requirements. For example, tasks related to entertainment applications may be better evaluated on OOD less difficult to detect than the one required to be detected in risk-critical tasks, such as medical applications. Second, its definition of OOD hardness was carried out with respect to ResNet 50, specifically equipped with softmax as its confidence function. This makes ImageNet O heavily biased. The box plots at the bottom of the slide illustrates this point. It visualizes the performance of 525 ImageNet classifiers on ImageNet O with higher values to the right, indicating better performance. As indicated by the orange arrow, ResNet 50, represented by an orange marker, has the worst performance by far, with a significant gap between its performance and that of the second worst mole. This clearly demonstrates the bias of ImageNet O. In this paper, we present a novel framework for generating benchmarks. Unlike other existing benchmarks, our technique is not biased towards any arbitrary mole, such as ResNet 50, or any specific confidence function, such as the softmax response. Furthermore, our technique generates COD benchmarks that cover a variety of difficulty levels. For more details about our proposed algorithm, we invite you to read the paper or scan this QR code for a brief video explanation. Next, we use our technique to generate COD benchmarks for 525 ImageNet classifiers. Each point represents an evaluated model. On the right, the red box plot shows the performance of these models on ImageNet O. To the left, we can see multiple box plots that depict the performance of these models across all severity levels. The first box plot to the left represents severity level 0, the easiest difficulty level. Let's illustrate what it means with an example. If the evaluated classifier were trained to classify a subset of butterfly species, for example, an easy-to-detect OOD class could be the class of flashlights. Severity level 0 is populated by such easy-to-detect classes. As we increase in severity levels, so does the difficulty of distinguishing the classes in the severity level from ID samples. Severity 5 represents the median difficulty level. In our example, an OOD class could be a hawk moth. Finally, severity level 10 represents the classes hardest to distinguish from ID classes. In our example, it might populate other butterfly classes that were not observed during training and are very similar to the ID samples. Note that as severity level and difficulty increases, performance degrades as intended. It's also worth mentioning that the unfair bias against ResNet 50 observed when using ImageNet O has not been observed in our results. The scale of our analysis has led us to make numerous interesting and previously unknown observations. Following are a few of these observations. First, we have observed that some models are inherently excellent at detection. Notably, a subset of VIT models achieves the best detection performance both in absolute terms and per model size, regardless of the confidence function used. In a related paper, also accepted to ICLR 2023, we also find that VIT models from this subset outperform any other model in terms of uncertainty estimation performance in an ID setting. Another well-performing architecture is the language vision model CLIP, which achieves good zero-shot detection performance. This means CLIP could be used as a zero-shot detection algorithm, allowing the user to change the definition of which classes are considered ID in a flexible manner without the need to retrain the detector. We also measured COD detection improvement when using different training regimes to explore whether a certain method consistently contributes to detection performance. Results are depicted in the figure on this slide. Of all the training regimes we evaluated, knowledge distillation had the most significant impact in most severity levels. In the aforementioned paper, we also find that among these training regimes, knowledge distillation is the best booster of uncertainty estimation performance in an ID setting. Another important observation is that the performance of a model and a confidence function pair should be considered with respect to the required severity level. Let's understand why this is the case with an example. The box plots on this slide show the improvement in performance when using the Odin detector algorithm instead of softmax. The green shaded area on the y-axis indicates the area of positive improvement by using Odin instead of softmax. As we can see from this figure, as severity increases, VIT's performance is improved to a greater degree by using Odin instead of softmax. However, for ResNet 50, the improvement provided by Odin decreases as the severity increases, and in the highest severity levels, its impact on ResNet 50 is actually negative. These were just a few highlights from the paper. The paper contains many more results, and we invite you to read it to discover more.